So, continuing with our discussion about the representations of different types of monosaccharides, we mentioned in the previous video that one of the common presentation for the linear structure is the Fisher projection, and that's the one where you draw it like this. And the way you draw this, it makes it look actually a lot simpler than what it would look like in three-dimensional space. For example, I've made a model here showing an example of what glucose would look like if it were to be in its linear form. All right, and like when you're looking at this, it looks like there's atoms all over the place. It doesn't look nearly as neat and tidy as this does right here. In this right here, you can see what looks like a bunch of carbon atoms put into a line. All right, and one thing you have to remember is that every, like this, and this carbon, those are all tetrahedral centers. All right, and that means they've got 4 groups going off in that tetrahedral arrangement. And when you do that, when you realize that every single one of these black atoms, with the exception of, so this is the aldehyde carbon at the top, every single one of these black atoms is going to have things going on, is going to have things arranged tetrahedrally. It's actually very hard to have this, to arrange this molecule so that these atoms would be in a straight line. All right, so if I were to try to do that, if I were to try to represent a model that showed this right here, what you would start to notice is that this thing actually starts to bend back on itself. All right, so I have to put my hand there so that you don't see the atoms behind it. So this carbon right here would be the aldehyde carbon. You can see that's the oxygen of the aldehyde, which corresponds to that oxygen right there. All right, and so if I go to the one next below that, all right, it would be this carbon right here. All right, and you can see that this carbon right here, I'll turn that right there. You've got this oxygen right here, which would be coming out towards you from this carbon in the center, and this hydrogen right here is going to be coming out towards you, but on the left side. All right, so those would this and this would correspond to this and this. All right, but what ends up when you're doing this, notice that the bonds that are shown vertically are always going back away from you. And if you do enough of those, if you made a model of that, you would realize that essentially, well, if these carbon atoms are constantly, if anything vertical is constantly going back away from you, you'd realize that it eventually is going to start to circle back on itself. All right, so it's a little bit more complicated when you make one of these models, but a model does help you. When you hold it, it helps you to see the three-dimensional nature of these atoms in space. All right, so recall that there's, with these monosaccharides, that this linear form can cyclize to make a cyclic form. All right, and we'll talk a little bit more about that later, but there is a convention for how you draw the cyclic form as well. So when showing the cyclic version of glucose, there's a convention in drawing that too. So to help out with that, I've made this model right here, and to make it a little simpler, I've removed all of the hydrogens off of the carbons. All right, so for example, every single one of these black atoms, we know that there's 4 bonds to each of those atoms, but I've removed the hydrogens so that it's a little easier to see the atoms in this. With the hydrogens on it, it's really difficult to see things because certain atoms are always obscuring your view of other atoms. All right, so in taking a look at this particular model right here, you'll notice that there is a 6-membered ring. All right, so that 6-membered ring, you can see it right here, and notice that one of the atoms in that 6-membered ring is an oxygen atom, which corresponds to this one right here. All right, notice in this version, I mentioned before that for this to be glucose, this hydroxyl right here at this position could either be going forwards or backwards. Notice here I've just drawn it going backwards. All right, so this would actually be what's considered the alpha version of glucose. All right, so whenever you are drawing the cyclic version of glucose molecules, So the common convention used when showing the cyclic version of the monosaccharides is what's called a Hayworth projection. All right, and essentially what you're going to do is you're going to essentially try to make this look somewhat three-dimensional. All right, so if I take this model right here and I turn it sideways, all right, so that we're looking at the ring on its edge. All right, you'd notice that some of these hydroxyl groups would be essentially below the plane of the ring, but some of these hydroxyls would be above the plane of the ring. So this hydroxyl, if I show it, if I put that hydrogen in that's missing, you'd see that the hydrogen attached to that carbon goes down below the plane of the ring, but the hydroxyl goes above the plane of the ring. Whereas if I focused on this carbon right here, the hydroxyl, you can see that the hydroxyl on that carbon is below the plane of the ring, where the hydrogen would be above the plane of the ring. All right, so what we're going to be doing is we're going to be taking this projection right here, and what we're going to be doing is we're going to be rotating the edge so that the bottom edge of the ring moves forward. Okay, so watch when I do this. These two atoms at the top of the ring are going to move backwards, and these two atoms at the bottom of the ring are going to rotate forwards. So if I do this right here, all right, so notice how these atoms down at the bottom are now closer to you, and these atoms at the top are now farther, from your perspective, would be farther away from you. All right, and that's what we're trying to represent here, is that the atoms down at the bottom part of the ring are going to be angled slightly towards you, all right, and the atoms at the top of the ring are going to be angled slightly away from you, all right, and we do that by, and if you think about this three-dimensionally, if you were to hold it that way, this right here these atoms right here would look larger to you than the atoms in the background, all right? So when you do this, on each different atom, you can show atoms either being straight up or straight down. Anything that is drawn in like this position, the ones that are above the ring are shown here, all right? So all of these positions right here would correspond to atoms that would be above the plane of the ring. Okay, and all of the atoms that are shown going down from the carbon atoms would be considered to be below the plane of the ring. All right. So if I was to show glucose, a common way that I can do it is to do just like this right here, where all I do is I draw this Hayworth projection, and when I show whether the hydroxyl is going up or down, just recall that that means that if there's a hydroxyl going up here, there's a hydrogen that's just not drawn there that's going down. Often when people are showing Hayworth projections, they will show both the hydroxyl and the hydrogen. So for example, when you're looking at this Hayworth projection of glucose, you'll notice that not only do they show the position of the hydroxyls relative to the ring, but they also have hydrogens shown on the opposite sides. All right, but there's plenty of times that, for example, when you look at this representation right here, notice that they save a little time by just not drawing in the hydrogens. But when you're looking at that, you would just realize that anywhere there's not 4 bonds to a carbon, there would be hydrogens in the last position. All right. So there's a fair amount of vocabulary that's involved in when talking about saccharides. One of these words that's commonly used refers to whether that sugar has 6 carbons or 5 carbons. All right. So most of the common sugars that we deal with, things like glucose and fructose, all have 6 carbons in them. All right. So for example, so another example is galactose. All right, so if you look at this, this is in its Fisher projection. There's 1, 2, 3, 4, 5, 6 carbons. All right, this is in its Hayworth projection. All right, so any monosaccharide that contains 6 carbons is considered a hexose. All right, but there are some sugars out there. For instance, this is ribose right here, and I've shown the 2 different forms of it right here. Only has, since it only has 5 carbons, generically those are called pentoses, and hopefully that'll be easy to remember. Pent is commonly a prefix for 5, having to do with 5. Hex is for 6. But notice one thing about the formulas here. They all have the empirical formula of CH2O. All right. So if you were to calculate count up the atoms in this molecule right here for a hexose, it would be C6H12O6. All right. Notice there would be twice as many hydrogens as carbons. All right. But if we were to count the formula for a pentose, the formula would be C5H10O5. All right. But so no matter how you do the formula, there's always twice as many hydrogens as there are carbons and oxygens. So when you refer to monosaccharides as pentoses and hexoses, that has only to do with how many total carbons there are. All right, but we can also classify different monosaccharides as either being an aldose or a ketose. All right, and this has nothing to do with the number of carbons. It actually has to do with the functional group that would be in the linear chain. All right, so if I go back to the earlier structure, okay, so the earlier structure of glucose, you notice in its linear form, before it cyclizes, it would contain an aldehyde at this position. All right, so this particular molecule actually occurs when an electron pair on this hydroxyl right here attacks that carbonyl on the aldehyde. All right, so in its linear form, it contains an aldehyde. All right, so therefore it's what's considered an aldose. All right, so an aldose is a monosaccharide which would have an aldehyde in its linear form. By comparison, some monosaccharides would have a ketone in their linear form. All right, so whether it has a ketone or an aldehyde, both of those functional groups have a carbonyl carbon. So that's what they have in common. All right, and that's what's necessary for the cyclization to occur. All right, but if that carbonyl is part of a ketone, such as this right here, that particular monosaccharide would be considered a ketose. All right, so the most common example of that is fructose, which hopefully you've heard about. And when fructose makes its cyclic form right here, that's going to be come from this hydroxyl right here, bending around and attacking this carbonyl carbon. Okay, so again, when fructose cyclizes, it's a matter of this hydroxyl right here, or the electron pair on this hydroxyl, attacking that ketone carbon. All right, and when that occurs, it's going to end up making the cyclic version here, which you'll notice is that actually makes a 5-membered ring. So, so far we've shown examples of monosaccharides that exist in a 5-membered ring variety and some that exist in a 6-membered ring variety. All right, and hopefully, and I understand that this can be a little complicated when you're first hearing about it. It would be really nice to say that this particular sugar always makes a 6-membered ring, and that this particular sugar always makes a 5-membered ring. But what makes this a little bit more complicated is that you can actually have the exact same sugar make either a 5-membered version or a 6-membered version. All right, in the classic example, and most sugars, most hexoses, which means monosaccharides that have 6 carbons in them, have a possibility to make actually both forms. All right, so a classic example is glucose. All right, so if glucose were to cyclize, where this particular hydroxyl right here is what attacks, kind of bends around, and again, it wouldn't really be this linear shape. These carbons are capable of bending around. All right, if that's the cyclization that occurs, you would end up making this variety right here. If this hydroxyl bends around, you end up making the 5-membered ring, which is called this is a furanose